All right, welcome back to Essential Perturbation Theory and Asymptotic Analysis, Chapter 5. Are there any questions before we jump into Chapter 5? Tonight I'll post solutions finally, got all the homeworks in, and I'll also post or describe the algorithm for the assigning the grades for the homework. And coming soon, maybe on Thursday will be your next homework assignment, okay? And I anticipate there won't be more than 3, and there won't be less than 2. Okay. So, Chapter 5 is, we're talking about my favorite problem in this whole area, matched asymptotics and boundary layer problems. So we've already encountered a couple examples of these. One was a very simple linear problem, and we used this, the solutions of that problem to motivate this concept of matching that we did in Chapter 2. But in Chapter 1, we introduce a very simple linear problem and a more complicated nonlinear problem. And we want to generalize what we talked about in there, look at lots of different examples, and kind of build a kind of attack strategy for looking at problems like this. As I said, this is my favorite topic in the whole of the book and the course. So we're going to follow a bunch of different books, and I'll pull examples out of books by Holmes and Hinch. This one is freely available to those at UT through Springer link. Kevorkian and Cole, I'm not sure about. That's also a Springer book. Miller is an AMS book, but it's a quite nice book. So again, we're going to go back to stuff we learned in Chapter 1 and Chapter 2 when we discussed matching. A lot of the terminology we've already settled on from Chapter 1, but I want to review what we did there with a very simple problem, kind of a motivating problem, to get our legs under us again. So let's get restarted with this problem. So for matched asymptotic analysis, you can study boundary layer problem or boundary value problems or initial value problems. I may throw in an initial value problem near the end. I'm not sure about that. But for the most part, we're going to focus on boundary value problems. And we're more than that, we're going to focus on boundary value problems of second order type. So 2-point boundary value problems.
Is there any particular reason that we choose boundary forming of initial value?
So both exhibit boundary layer phenomena. And they're intimately related to each other, right? So the idea of a boundary value problem versus a boundary initial value problem, it can be thought of like this. If I have a second order boundary value problem, then I'm going to have, or let's say second order initial value problem, then I'm going to have at my initial condition, I'm going to have both I'm going to be specifying both the value of y and its derivative. So that's a little bit like specifying, starting off with the value of y, and then one way of doing it, or one way of thinking about it is, well, okay, so we specify a value and a derivative, right? There's our derivative. And so the solution goes off and looks like this. And if we have some sort of terminal value in sight, terminal time, I guess in this case, then it hits over here. So you've probably heard of this numerical method called the shooting method. And the idea is, suppose I want to figure out what is the solution of a boundary value problem, but I only have a code that works for initial value problems. How can I make it work? Well, what you do is you let's say you know what the initial value is here, and you know what it should be over here, or what the final value should be. Now, for this boundary value problem, which connects this point to this point and satisfies an ODE like this, there's some initial slope, but you don't necessarily know it. It's not specified for you. So what you can do is fix the initial value and vary the slope. And when you shoot across, you're going to get solutions which look like this. If you might shoot with a lower angle, you get something like that. Okay, it's analogous to the ballistics problem of shooting. So that's why it's called the shooting method. If I shoot a little higher, I might get something like that. So initial value and boundary value problems are intimately related to each other. If you pick just the right angle for your initial value problem, you'll hit at the final condition that you actually are looking for. So you can use that as a numerical method, but you can also use it to see how intimately related initial value problems and boundary value problems are. So they're not really different from each other. So if one exhibits a boundary layer or boundary value, or sorry, if one exhibits a boundary layer phenomenon, then the other is going to as well.
But I thought like boundary problems may not have existence of solution.
Go, say again?
Like solution, like existence of solution of like a boundary value problem is not guaranteed.
That's true. Yeah, we'll talk about that. Okay, so sorry for that digression, but we're going to mostly be interested in problems of this type, where we specify an ODE. We're going to start off with linear ODEs, and where we have two what are called Dirichlet or Dirichlet type boundary conditions, where we specify the values of the function at some point here and some later point. So I'm going to view this as being X, but I'll often stumble into the term where this is viewed as time. And if I'm viewing it as a time interval, then I'm going to view these as being like trajectories. Okay. So I might say, I might stumble into the idea of initial time and final time. Okay. But usually we're talking about spatial problems here. One way of viewing this is if you do, how many of you know of something called the heat equation? Heat equation. So the heat equation is a parabolic differential equation, right? And you can even add a source term onto it. Suppose that we're only in one space dimension, then the heat equation reduces to something which looks like this, maybe some diffusion constant times U double prime. Okay. Or actually, I still need to use partial derivatives because there is a time derivative floating around. So that's two simple derivatives of X. So if I look for what's called the steady state solution, this usually comes, by the way, with an initial condition and also boundary conditions. But if I look at the steady state solution, then it solves a problem which looks like this, a pure boundary value problem. Okay, the steady state solution is whenever the time derivative vanishes. There's no time dependence. That's another way of looking at these problems. So for the most part, I'm going to view X as being a spatial coordinate. Right? In this case, I have a linear constant coefficient boundary value problem, but epsilon is a small parameter that's going to 0, essentially. So we're losing this higher order term. And it's singular. We call it singular because we're losing the highest order derivative. And it's called regular if we lose a lower order derivative. Now, if I lose this, if I just cross this highest order derivative out, there's a problem because I have two boundary conditions, but I only have a first order ODE. The solution to a first order ODE cannot in general satisfy both boundary conditions. All right, but this problem nicely has an exact solution. So let's see what that solution looks like and see what are its characteristics as epsilon gets smaller and smaller. The solution, the analytic solution of the last problem is given by this function, similar to one we've seen before. R1 and R2 satisfy this quadratic equation. So there's no explicit form for what R1 and R2 are. Well, there's no simple form for R1 and R2 without the radical, I should say. Otherwise, it's algebraic. So let's see what does this solution look like as epsilon gets smaller and smaller. You can see R1 and R2, the solutions of this quadratic equation, or not, the solutions coming from this quadratic formula, I should say, are given in terms of epsilon, but there's no clear formula for it otherwise without the radical. So here's what solutions look like as epsilon is made small. As epsilon gets smaller and smaller, basically we keep the structure of this outer solution, but if epsilon is really small, we have a very sharp boundary layer. This one is not so sharp. It's only for epsilon equals 0.1, but if we go epsilon 0.01, then it's going to look more like what I drew just there. So the boundary layer, we say, is here at the left-hand boundary point, okay, at x equals 0. So the question is, why doesn't it form in the middle? Why doesn't it form at the right-hand boundary condition? So that's a good question. Why is it forming over here? Is it always going to form over there? The answer to that question is a resounding no. In fact, we saw in our nonlinear example from chapter 1 that we had a boundary layer that formed right in the middle. Okay, so boundary layers can form anywhere. We want to come up with some sort of quantitative way of understanding where a boundary layer is going to occur and then how to analyze it, how to get solutions to problems like this. So remember that we had this process that we outlined in chapter 1, and I'm going to review it now, but I'm not going to, I'm going to pretend like you guys remember what happened in chapter 1. Maybe you do vaguely. We partitioned up the domain into what we called an inner and outer region. So the outer region is where the boundary layer isn't. So that's going to be this region over here. We're going to call that the outer region. And this region here near the boundary layer is going to be called the inner region. But the inner region is going to be scaled by epsilon, as we'll see. And it will shrink as epsilon shrinks. So let's look at that outer layer. Yes, question?
Yeah, so how to understand that if there is a fixed point besides the both sides, there can be boundary layers. Is that following that on a fixed point theorem, like the contraction mapping?
No. No, the location of the boundary layer is dictated by the structure of the equation. And we're going to figure out a kind of algorithm for finding out, ascertaining where the boundary layer should form. Okay, so the reason the boundary layer forms here and not here or anywhere else is precisely because this, the structure of this multiplier, this term here. The fact that this is a 2 and not a -2 means that we're going to have a boundary layer at the left. If it was -2, it turns out it's going to be at the right. If it's some function which has a simple 0 in the middle of the domain, then we're going to have a boundary layer in the interior. So basically, all of our analysis is going to come down, at least for the linear case, what does this guy look like? Here, it's a positive function. It's just the constant 2. So the boundary layer ends up forming at the left-hand side. So the outer area, we're going to have something called the outer solution or the outer expansion. So the outer solution is going to be active away from the boundary region. And so we're going to denote that region by x1 up to 1, where x1 is some number, we don't know what it is, between 0 and 1. It doesn't really matter that what this x1 is. We're going to assume that it's something, it's order 1, and we're going to have the outer version of the solution having a valid asymptotic expansion out there of that form. Here we're going to assume that it's in simple asymptotic power series in terms of epsilon powers. Simple epsilon powers, epsilon to the first, second, and third, and so on.
When you say X1 is of order 1, do you mean it doesn't depend on epsilon?
I'm going to think about, yes, right. So I'm going to think about x1 being some fixed number. And so the outer region is everything between x1 and 1. Yeah. And I'm going to assume that I have an expansion for the representation of the outer solution in terms of this asymptotic power series. What we're trying to get is a description for the solution in this part. Okay, we want to describe that. And this is the part that's changing a lot as epsilon changes. So we want to kind of stay away from that for now. All right, so we know that the boundary layer is at the point x equals x naught. That's something that we know because we know the true solution. In general, we're not going to know the true solution, so we're going to have to find out. We're going to have to find techniques for locating it. We're going to assume also that y out, the outer version of the solution, has a first derivative and a second derivative that also have an asymptotic expansion, and the asymptotic expansion is given as the derivative of this asymptotic expansion term by term. Okay, so you can see that this is just the term by term derivative of that asymptotic expansion. The same with the second derivative. So we're going to assume that those are valid. Now we're going to substitute them into the equation and see what happens. So if we substitute these into the equation, we have the first term, the equation, that's just epsilon times the second derivative. Second derivative, we just do a dump of all of this stuff in for the second derivative. Likewise, for the first derivative, we're going to dump this asymptotic power series. And for the 0th order derivative, or the function itself, we're just going to dump in the original asymptotic expansion. When we add those three things up, that's going to be asymptotic to 0. But we can view 0 as being something kind of special. It's not just 0, it's 0 plus 0 epsilon plus 0 epsilon squared. Okay, so in other words, this is an asymptotic power series expansion, and all terms are equal to 0. So now all we're going to do is equate terms with like powers of epsilon. So let's figure out what the first one should be. The first thing that we can construct is an order 1 equation. So the order 1 equation comes from, let's see, there are no order 1 terms in this first box here. There is an order 1 term here and here, so that's going to contribute to the first equation. Both of them have a 2 in front of them, and so I'm just going to divide out that 2, because I'm going to set that equal to the term on the right-hand side, which is just going to be a 0. So this is my order 1 term on the right-hand side. That's where I get y0 prime plus y0 equals 0. So the 2 I've divided out on the left-hand side, and I can just get rid of the 2 essentially because there's a 0 on the right-hand side. Now we look for the next order equation. That's going to be the order epsilon equation. How can I build that? Well, the order epsilon terms on the left-hand side are going to be epsilon y double prime. Epsilon y0 double prime. It's important to note that this is y0. Plus 2 epsilon y1 prime plus 2 epsilon y1. And those are all going to be equal to 0, the order epsilon coefficient on the right-hand side. Well, I already know what y0 is, presumably from solving the order 1 equation. So I'm going to throw that over on the right-hand side with a minus. And then when I divide by 2, I get minus 1/2 y0 double prime. So here's how this goes recursively. Once I know y0, then I can compute y1 knowing y0. Once I know y1, I can compute y2 knowing y1. That's the recursive nature of improving these terms or gaining more terms in this asymptotic power series expansion. Are there any questions about building this sequence of equations? The next step is to figure out what are the boundary conditions. Well, I know that the boundary layer is at x equals 0, and the outer solution is staying away from the boundary layer. So the boundary condition I'm going to use is just the boundary condition at x equals 1. But it's useful to know how both boundary conditions transform. So the boundary conditions can be written like this. y0 equals 0, and y of 1 equals 1. But remember, I'm assuming that I have a valid asymptotic expansion of both of these functions. So this is going to be y, presumably something like y, y0 at 1 plus y1 at 1 epsilon plus y2 at 1 epsilon squared. I can do this for both the right and left-hand boundary conditions, although one of them is not going to be valid. So this one is not going to be valid, so we're going to reject that because that is in the boundary layer. We want to stay away from the boundary layer and only work in the outer layer, outer solution region. Okay, so this is the boundary condition we want to use. But this tells us that y of 0 has to be equal to 1. Y of 1 at 1 has to be equal to 0. So we think about this 1 as being an asymptotic power series expansion. So its order 1 term is 1, but all its higher order terms are 0. So that gives us this sequence of boundary conditions. Y1 at 1 is equal to 1. Y1 at 1, I said Y0 at 1 is equal to 1. Y1 at 1 is equal to 0, and so on. Now, these ones over here are not valid because they exist in the boundary layer. So we have to reject those as boundary conditions. So we're only going to enforce the boundary conditions at x equals 1 because the boundary layer is at x equals 0. So now let's solve the order 1 equation. So the order 1 equation is here. The very simple solution to that is y0 of x is equal to c0 e to the minus x, where c0 is a constant that we have to determine. We already have a boundary condition that involves y0. That's y0 at 1 equals 1. Now, you might not like this because this is like solving a first order boundary condition or first order problem with a boundary condition that is on the right. So basically, we're looking at solutions which look like this, right? They're coming in like that, and we can only select one of these based on the choice of our boundary condition, which is on the right. Normally, with an initial value problem, you're looking at boundary conditions which are on the left. In other words, the boundary condition, when I view it, is on the left-hand side. But actually, for initial value problems, that is problems that only have one boundary condition, I can solve these problems either from the right or the left. It doesn't matter. So I can have a boundary condition for these problems where the boundary is to the left, or sorry, to the right of the solution. So the solution is existing over here, and the boundary condition is over here. Okay, so it's kind of like an initial problem where we're running time backwards. Does everyone understand that? So we're using a boundary condition that is on the right-hand side. So if we plug in x equals 1 for this general solution, we find that c is equal to e to the 1. So we can substitute that back in, and we find that our general solution for this first order, or for the leading order term, is just going to be y of 0 e to the 1 minus x. All right, so this determines a leading order solution completely and uniquely. There's nothing else more to do here. So that gives us our leading order term. We can now move on to the first order correction. So that's the y1 term. So that satisfies the following equation: y1 prime plus y1 equals minus 1/2 e to the 1 minus x. So where does this come from? Well, we have to take two derivatives of this guy, right? Minus 1/2 y0 double prime x. Right, let's see if I did this correctly and didn't make any mistakes. Let's see, this one here is a mistake. Does anyone else see the error? Or maybe there's not an error. No, okay, there's not an error. So I need to I have y0 x is equal to e to the 1 minus x. I thought it took the derivative incorrectly. So when we put it on the right-hand side, we have to take two derivatives of that guy. All right, so the first derivative is going to be what? It's going to be e to the 1 minus x times minus 1, right? And the second derivative is e to the 1 minus x times 1 minus 1 again, 1 minus 1 squared. So I think I did get it okay. So that's what goes on the right-hand side. So this is the equation we want to solve. And I'm going to try a homogeneous part and a particular part for this. The homogeneous part, that's just the solution to this set equal to 0. That's exactly the same as it was in the leading order term. So that's just going to be a constant times e to the minus x. Now, for the particular solution part, we're going to guess the following form. We're going to guess, because this is something a bit more complicated over here, we're going to guess C1P, so that's a constant for the particular solution, times x times e to the minus x. Now, the reason we have to do this is because this is essentially a constant times the homogeneous solution already. So in order to get this type of term, we need to guess a particular solution, which is slightly more complicated. And there's a basic algorithm for choosing this. And the algorithm says, well, if you have something which looks like a constant times a homogeneous solution, just multiply that times x and set another constant. Yeah, I guess so. I call it the method of homogeneous and particular solution, but I think there are various names for it. Okay, so we need to determine these two constants. So we're going to plug this guessed form back into the original equation and just solve for the constants that we need. And we're going to use the right-hand boundary condition, y1 of 1 is equal to 0. So from that, we obtain y1 is equal to 1/2 1 minus x e to the 1 minus x. So now we have a leading order term and a first order correction. So we have y0, we have y1. Both of these are determined exactly using the right-hand boundary conditions at x equals 1, and they're completely determined. The next thing we want to do, you recall probably, or maybe from chapter 1, is we want to determine the thickness of the boundary layer. What I mean by that is we want to determine how this scales, the solution is going to scale with epsilon, or in particular, how the inner solution scales with epsilon. To do this, we're going to introduce a stretched variable, something called a stretch variable. And I call my stretch variable always z. And in this case, it's going to be x over delta. Now, in general, it's going to be x minus the location of the boundary layer. But here, the boundary layer is located at x equals 0. So it's x minus 0 over delta. Delta is a function of epsilon that has to be determined. And the way we determine it is through what's called the principal dominant balance. which we'll get to in a moment. The second thing I need to define is something called the inner solution variable, the dependent variable. So that's what I call capital Y of Z. Capital Y of Z is just equal to little y of Z times delta times Z. Basically, we're just, and you can see this is just X. So this is nothing more than a representation of the solution that's going to be, or going to be assumed to be valid in the inner solution region. So the inner solution region is that region near the boundary layer. Now, in this principle of dominant balance, which I'm going to do momentarily, I need to have the differential equation completely reconfigured in terms of this capital Y function. So I need to replace the ordinary derivative dy dx and d2y dx squared with the versions that are valid in the capital Y variable with the Z independent variable. So I need to transform those using the chain rule. The first derivative transforms as 1 over delta dy dz, and the second derivative as 1 over delta squared d2y dz squared. Okay, so the equation as a whole, the original equation that I was dealing with, transforms like this. Now, the whole point of determining the boundary layer thickness and using this method of dominant balance is to get rid of the singular nature that we experienced before in the equation, sort of transform that. And we argued why this had to be so in chapter 1, first by demonstrating this whole principle in the context of algebraic equations and then moving it to differential equations. Okay, so here's the new equation that we want. We're going to use principle of dominant balance to figure out what delta should be. Here's the idea of dominant balance. We're going to assume that y and both of its derivatives, the first and the second order derivatives, are order 1 when it's expressed in the proper inner variable. Or in other words, when it's in its proper stretched variable, when we've chosen the proper stretching parameter delta, then these are going to be or experience order 1 change in the boundary layer. Okay. Now, the second part is we want to then take the coefficients that we see here, especially the coefficient in front of the first term, and we want to asymptotically balance that with one of the other two terms in such a way that when we balance those two terms dominate in terms of epsilon as epsilon goes to 0, the third term as epsilon goes to 0. All right, so that's what I've expressed here. The derivatives in y are all order 1. The coefficient of term 1 and one other term must balance in the asymptotic sense and must dominate the remaining term in the limit as epsilon goes to 0. Dominating means must be a lot bigger than. All right, so we have the following possibilities for dominant balance. Terms 1 and 2 of equation 8 balance. So this means that the coefficients have to equal in the asymptotic sense. Well, here we can just set them equal in the real sense, but neglecting the 2. The 2 is not necessary. So that means that we have epsilon over delta squared is equal to 1 over delta. Epsilon over delta squared is equal to 1 over delta. If you solve for delta, you find that the value of delta is then equal to epsilon. In this case, terms 1 and terms 2 are order 1 over epsilon. Now, as epsilon gets small, that means those get big. And they dominate term 3, which is order 1 as epsilon goes to 0. What's bigger, order 1 over epsilon or order 1 as epsilon gets bigger? Order 1 over epsilon. So terms 1 and 2 will dominate term 3. So that is a viable situation for dominant balance. The other one is not going to be viable, but let's check it anyway. In this case, terms 1 and terms 3 of equation 8 balance. So that means epsilon over delta squared is equal to 1. It doesn't matter that this is a 2 here. I only need their asymptotic balance. So that's that equation. Epsilon over delta squared is 1. that means delta is equal to square root of epsilon. In this case, 1 and 3 are order 1, and they don't dominate term 2 because term 2 is going to be order epsilon to the minus 1/2. That gets really big as epsilon goes to 0, certainly not dominated by order 1 terms. So this is not a viable situation for dominant balance. So for dominant balance, we're going to choose delta equals epsilon. That sets the thickness of the boundary layer. And furthermore, it sets the equation. So the new equation is going to be something like, I think it was, this is going to be 1 over epsilon here, 1 over epsilon, 1 over epsilon here, 1 over epsilon here, and then order 1 here. Okay, so I'm going to take that 1 over epsilon, and I'm just going to multiply the whole equation through by epsilon. Because I'm allowed to do that, that doesn't change anything. So if I multiply through by epsilon, this is the equation that I'm getting in the inner solution region now. And you can see that this equation here now is no longer singular, because whenever I set epsilon equal to 0, I lose a lower order term. So this becomes a regular perturbation problem. Now I'm going to assume, as I did before, that y in the inner region, when expressed in this capital Y variable with the independent variable z, has some asymptotic power series expansion that is valid. And I'm furthermore going to assume that the derivatives also have asymptotic power series expansions that are equal to the term by term derivatives of the sequence I had above. So this is not always the case, by the way. If I have an asymptotic series, and if I take the derivative of both sides of that, that may no longer be valid. So just so that you know, if I have something like this, and I take the derivative of both sides with respect to x, you might ask, is then the derivative equal to the derivative, term by term derivative of the well, is this derivative function represented by this asymptotic power series? The answer is that's not generally true. So if you go the reverse direction and integrate, it always is true. I can integrate term by term an asymptotic power series and get an asymptotic power series for the result, but I can't differentiate. I can't go the forward direction. However, if you just assume that it's valid, you're okay. Well, you're not.
Is there a condition that can guarantee that?
Yes, there is a condition, and I forget it actually. But I should probably put that in the notes, and we'll probably do so at a later time. But there is a simple condition that you can check for that. It's not on the top of my memory. Okay, so I have these asymptotic power series expansions, which are now going to be valid for this regularly perturbed problem, and I'm going to dump them in, and I'm going to do my term by term manipulation as before. This time I only have one boundary condition, and that's the boundary condition on the left. This is a problem, though, that you might see right away. The problem is this is a second order linear ODE. It either needs two initial conditions or two boundary conditions in order for me to solve this problem exactly. But let's not worry about that quite yet, because there is going to be a way that we can determine these things exactly. For now, we're just going to throw in our expansions into the equation, and then we're going to do our regular perturbation analysis as before. Well, actually, we did a singular perturbation analysis in the outer solution region. We're going to do regular perturbation analysis here with the inner expansion. So we need to form an order 1 equation. So what are our order 1 terms? Order 1 terms are going to be y0 double prime plus 2y prime is equal to 0. So that's the first equation. The second equation is y1 double prime plus 2y1 prime is equal to minus 2y0 without any prime. Is that correct? Yes. So that's going to be given by this term, and that term. But this guy is a known thing, so I'm going to move it over to the right-hand side. And similarly for the third order, or so this one is usually called leading order, first order correction, and then second order. So how do the boundary conditions transform? Well, we definitely now know that we only have one boundary condition to apply, and that's at x equals 0. Remember, y of 0 is equal to 0. Little y of 0 is equal to 0. So you have to transform everything. So what is the value of z at x equals 0? Well, z is equal to 0 whenever x is equal to 0. I'll say it like this. Right? So y at 0, what is that going to be equal to? Well, we said this is just equal to y of epsilon times z. Okay, but z is equal to 0, so that's just epsilon times 0, so that's equal to 0. So that's how you find the boundary condition for capital Y0. And then you do a power series expansion for Y0, right? Asymptotic power series expansion. You're going to pretend like this 0 is really a power series expansion, just 0 with all terms. And so that tells you what these terms, what are the boundary conditions for each one of these terms. Okay.
Someone raised their hand.
Okay. Question?
Is there any reason on the last slide why the order 1 terms aren't y0, they're just y?
Let's see. Ah, that's an error. Thank you. Very good. This should be, that should be 0. So that was your question, correct?
Yes, thank
Great,
you.
thank you. That is a typo. And now it's okay? Understandable now?
Yes, thank you.
Great. Thank you for pointing out that error. All right, so now we can pair these things up. We'll take this order 1 equation with this order 1 boundary condition. Too bad there's not 2, but okay, there's only 1. We'll deal with it as best we can. So our leading order inner term, that is y0, the equation is given here. So it's not hard to see, going back to our days in differential equation, to see that the solution of that equation is C0, 1, that constant, plus another constant times e to the minus 2z. Does anyone remember how to do this? How did I do this construction? So you just, so here's your equation. You're going to guess a solution of the type y0 equals e to the rx, right? And then you form a quadratic equation in terms of r, and then you figure out what the r's are going to be. There's 2 r values that you'll get when you solve that quadratic equation. It just so happens that when you solve that, in this case, you get r equals 0 and r equals minus 2. So those are the 2 linearly independent homogeneous solutions to our equation. We have 2 arbitrary coefficients or unknown coefficients. Now let's apply the boundary condition, the only one that we have, y0 is equal to 0. If we do that, then we find out that C01 is equal to minus C02. So in other words, this is equal to the negative of that. So I'm going to just collect them both into this constant C0. So this constant, which has to be determined somehow, is still present. One of the boundary conditions is satisfied, but otherwise the solution is determined up to that constant. So y0z is C0, 1 minus e to the minus 2z quantity. We're going to leave this C0 undetermined for the moment because we have no way of determining it yet. And it's going to be determined using matching. So let's do the first order correction. So what was the first order correction? It satisfied this ODE, y1 double prime plus 2y1 prime is equal to, I think it was minus 2 times y naught without any derivatives. So it's this equation here, minus 2 times y naught is what appears on the right-hand side. There's my y naught. So there's my right-hand side. So again, I'm going to guess a homogeneous solution and a particular solution. I know what is the form of the homogeneous solution. That's just what it was for the last equation. It's going to be some constant with no exponential term plus another constant times e to the minus 2z. That's the homogeneous solution. Now, what is the form of this solution over here? We can use the, what was the name you called it? The method of undetermined coefficients. So we just have to guess the right form of the particular solution and plug it in and hope it works. If you guess wrongly, then you're going to guess something else and try again. So the form that I'm going to guess is going to be alpha z e to the minus 2z. That's because there appears here a term which was also a homogeneous solution with a constant. In fact, it's kind of like both of them appear. This one's just a constant. That's represented in the homogeneous solution. And this a constant times e to the minus 2z is also represented there. So what I'm going to do about that guy is I'm going to set, and this might be a little bit overkill, but I'm going to multiply z times the second homogeneous solution, give it a generic constant alpha, and I'm going to introduce beta 1z and beta 2z squared to take care of the fact that I have a constant appearing over here. All right, so if I insert those guess form into the equation and solve, then I get a solution which looks like this. Okay, so the homogeneous solution or the particular solution simplifies quite a lot. I just get a z e to the minus 2z and just a constant. So, well, let's see. Did I do that? Oh, no, sorry. It's a linear term, c0z times that. That's the linear term. So this guy this guy stays around, this guy vanishes. I guess to be really careful, I maybe should have added a beta 0 term as well, right? But that would just vanish, right? I'm taking derivatives, wouldn't survive. It wouldn't survive the first derivative operator. Okay, so what do we have? There's our generic solution. We have two constant which need to be determined. This is the constant from the previous solution, so that there's nothing we can do with that. We're just going to leave it as is. All right, so using the boundary condition that we have for y1, we're going to find out that, so let's see what happens. This term goes away completely because z is equal to 0, right? If I plug in z equals 0, this term goes away completely. And then it's back to the same situation as before. As in the leading order term, I find the first is equal to minus the second. And I'm going to call that minus second equal to C1, just with one subscript. So here's now the general solution for my first correction, first order correction y1. Any questions about that? So I have two coefficients, C1 and C0, that have to be determined. And the only way that I can possibly determine these is via matching. So let's do some matching. Now, I introduced this process in chapter 1, The idea was, or sorry, chapter 2. We used a very simple matching procedure in chapter 1 and a refined matching procedure in chapter 2. Now, we weren't talking about matched asymptotics from the point of view of applying them to singular perturbation problems. We were just talking about a solution that we knew a priori, and it had this certain structure, and we determined how to match the two structures, the inner solution and the outer solution. It wasn't in the context of differential equations. So matching is something that that applies sort of in a standard way. For example, if I have a problem like this, or I have an equation like this, y of x epsilon equals x plus e to the minus x over epsilon, right? So suppose I do an asymptotic expansion of this. Okay, if I do a simple asymptotic expansion, deriving the terms as we did in chapter 2, you're going to find that basically this term falls out doing a regular asymptotic expansion. Then when I do a transformed coordinate expansion, where I make this order 1 variable, perform what's called an inner solution or an inner expansion, then I get something which essentially leaves this variable out. And then I have to match the two. So that was the procedure we did in chapter 2. It had nothing to do with the context of differential equations. You can take a function that cannot be described uniformly by an asymptotic series on an interval. And this is one example of that. Okay, so let's get to the point at hand, though. So now we want to introduce what's called an intermediate variable, W. And W is by definition x minus the location of the boundary layer, but here it's equal to 0, so it's x minus 0. So x over eta. But recalling that x is equal to z times delta, then that can be written like this. And so this is a formula we'll need later to put in our pocket. Now we need eta to satisfy a couple of properties. First of all, eta of epsilon should be a positive function of epsilon. Second, eta of epsilon should go to 0 as epsilon goes to 0. And delta of eta over eta of epsilon should go to 0 as epsilon goes to 0. In other words, whatever scale we have for delta, this eta scale should be kind of dominated by it. So here's an example. So if I have delta equals epsilon, and I have eta equals epsilon to the 1/2, so I'm talking about domination in terms of this power is bigger than that power. In fact, actually, this number is bigger than that number, right? As epsilon goes to 0. But notice that if I do that, delta over eta, that's equal to epsilon over epsilon to the 1/2, epsilon to the 1/2. That goes to 0 as epsilon goes to 0. Does everyone see that? So that's the kind of thing that I'm interested in. Now, delta is equal to epsilon in this case. So we know we're going to have to be operating with etas, which are of these sorts of scales. The power on epsilon, if eta is to be represented as a power of epsilon, has to be smaller than 1. In fact, it might be like 2/3 or 3/4 or 1/2 or something like that. All right. So, in fact, what we're going to show is that as you match to higher and higher order, this gets closer and closer to 1. The power that we require here. That was called the width of the matching scale that we discussed in chapter 2, but that's a long time ago. Okay, so those are the 3 things that we need eta to satisfy. And you can shorthand this with just a one-liner like this, that both delta and eta are positive. Eta of epsilon is bigger than delta significantly. Remember, this is like epsilon to the 1/2, this is epsilon, and both are significantly smaller than 1 as epsilon goes to 0. So that's what this terminology means. Okay, in fact, This is just a shorthand representation for all of this. Any questions about that? So we're introducing an intermediate variable and an intermediate scale. Delta is called the boundary layer scale. Now, what do we have so far? We know what is the boundary layer thickness. We have two terms of the asymptotic expansion. Actually, I don't have to write it because it's written down here. We have at least two terms in the asymptotic expansion for the outer solution. And we have two terms in the asymptotic power series expansion for the inner solution. We have that determined. The whole idea of matching was, well, what we're going to do is recast X for the outer solution in terms of that intermediate variable. Okay, I forgot to drop this guy here. X naught is just equal to 0, so we don't have to include that. Okay. So what I'm doing is I'm taking the outer expansion up to the first term. So just the leading order term and the first order correction. That's leading order, first order correction. Just two terms. And I'm going to rewrite those two terms in W times eta because X is equal to W times eta. X equals W times eta. Now what I'm going to do is I'm going to do some sort of expansion technique on this as epsilon goes to 0, and I'm going to keep all the terms which are smaller than little o of epsilon. And I'll show you how this goes. W is supposed to be assumed fixed, some sort of order 1 value, just like Z is an order 1 value. I'm going to do the same thing with the inner solution expansion up to order 1. So I have the leading order and the first order correction for the inner solution expansion. I'm going to write those in terms only of W, eta, and delta. So in other words, I'm going to get rid of Z and just going to write it in terms of W. Okay, and then I'm going to do some sort of expansion technique and only keep terms order up to little o of epsilon. As epsilon goes to 0, and W is assumed to be a finite fixed number. Okay, so this is the procedure. And it's a little bit abstract at this point. We're going to make it so second nature that because we're going to do so many examples that it'll just be, yeah, okay, that's what you do.
So the intermediate variable is the variable that we try to match the outer layer and
Okay, so so do I have the picture back? Maybe I have to move too many slides back. Okay, so I have my solutions, right? So I have an inner solution, which looks like that. It's kind of dive bombing. Outer solutions look like that. The outer solution is fixed completely, but the inner solution has some free parameters associated to it. So it could be like this, be like this. It's coming out of the boundary layer with some options. But now there's some intermediate range. This is called the intermediate variable range or the matching zone, where I want these two things to match up. So this is where W is order 1. So I'm going to look for an overlapping region where I can match these two functions together. And this is the whole idea of this intermediate variable. This is going to be order 1 in some sort of intermediate zone. And I'm going to try to match up these two solutions in that zone. So it's kind of somewhere nebulously between the outer solution region and the inner solution region. Okay, remember these guys, it's kind of like they don't touch, but actually they do have a little bit of overlap. Okay, so don't think about them as not touching, think about them as touching on a region which is going to start shrinking. All right, and I want to try to do my best to match them up over that shrinking region.
So we have some degree of freedom of the inner solution.
Yes.
Does that come from the fact that we have y0 equals 0, but we don't have any like, because there's like two integration concepts and we have one fixed by the left hand side and we say 1 degree of freedom. Is that comes from the coefficient there?
Yeah, so the matching is out here in the outer solution region, the solution is completely determined. There's nothing flexible about it. The inner solution is still has free parameters associated to it, right? So we're going to try to use matching to determine those free parameters because it only had one boundary condition for second order boundary value problem, or for a ODE of second order type, we only had one boundary condition. Therefore, we still have some degrees of freedom left open. So it's the matching procedure on this intermediate range, which is designed to nail down those unknown parameters. Before in chapter 2, we didn't have any unknown parameters. Whenever we were dealing with this function here, there was nothing unknown. We were just doing matching for matching's sake. All right. We were trying to come up with a uniform composite solution, which was asymptotically valid across the whole domain. But if we just do this sort of without matching, then we're only either going to get a solution which is valid in an inner region or outer region, but not both. Are there any questions besides that one? This is a key step, so if you have any trouble with it, make sure you ask your question. All right, so now this is what I just explained in words. Here it is in symbols. We want to determine, this should be W here. It is W, but I wanted to show an explicit replacement. So this guy should be just W. So I want to determine, okay, I left off one key point. When I do this expansion and then keeping only terms which are smaller than little o of epsilon, then what remains is what I'm going to call the match 1-1 out solution. Okay, lots of words. The outer match solution. Same thing down here. When I do this expansion down here and keep only little o of epsilon, or terms which are smaller than little o of epsilon, then what remains is what I'm going to call the 1-1 inner match function. Now, this guy here, the inner one, is still going to have free parameters. And those are going to be associated to the constants that I had in constructing y0, y1, c1 and c0. So now I want to make these two exactly equal to each other. So I didn't prove a theorem saying why that works, but it works. So I'm still searching for a good theorem that I could put in the book and show why this works in a rigorous sense. But I think most of you don't care anyway. You just want to know, you want to see how it works, not know why it works. So I want to choose those free parameters so that these two things match. And when they do match, I'm going to call their matching value the y1-1 match function. Then, to obtain a uniformly valid composite approximation over the entire interval, I can do that by adding up the outer solution plus the inner solution and subtract off from it the matching solution. Remember that? So we take the outer solution, add to that the inner solution expansion, only up to the first order term, first order correction, and we're going to subtract off whatever matches, because if we don't do that subtraction, then we're going to get double counting. Because both of these have in them, the outer and inner solution have this guy somewhere buried in its DNA. So since I'm summing them both up and making them valid on the same region, I have to subtract off that so I don't double count. Then I'm going to expect that the difference between my exact solution to that ODE and this uniform composite expansion is going to be a big O of epsilon squared, okay? Because I'm keeping the 1-1 term, so I'm going out to first order in each one, then the difference between this and this is going to be the next order term, which is missing, The next order term, which is missing, is going to be the order epsilon squared term. So all that remains is to figure out what the heck this matching term is. So let's dive into that. Okay, so this is going to seem a lot similar to what we did in chapter 2, because at least for this part, it actually is. So here's our outer expansion, keeping only the leading order and the first order correction. E to the 1 minus x plus 1/2 1 minus x, e to the 1 minus x times epsilon. Okay, so now I'm going to do what I said, because I always do what I say. I'm going to replace x and x in this instance with omega times eta. And I'm not worried about what eta actually is. That's going to sort of determine itself, and it doesn't have to be nailed down exactly. What is the eta scale? All right, so if I put that in, everywhere you see x, you're going to see now w times eta. W is an order 1 variable, and w in this case is going to be positive. So those are the two things to keep in mind, order 1 and positive. And so I can write things as, I'm going to pull out e to the 1 minus x out of both terms, okay? So I'll just have e to the 1 minus w eta times the quantity 1 plus 1/2, 1 minus w eta, that's coming from the x term here, times epsilon. So this is pretty straightforward. So this term here is an exponential. It has a very simple Taylor series expansion. Now, keep in mind, I'm trying to do an expansion as epsilon is getting smaller, but what do I know about eta as epsilon gets small? What happens to eta as epsilon gets small? It's also getting small. So that was by our rule, right? Eta gets small as epsilon gets small. Or if you want to think about it in this term, in these terms, it's much, much smaller than 1 as epsilon goes to 0. Okay, so I'm just going to do a regular Taylor expansion of that, keeping in mind that eta is going to be small, times this expansion here. This is already good enough for me. I just want things which are algebraic. So think about this. What I'm trying to do is get expansions which are algebraic in terms of eta and epsilon. Just powers of eta and epsilon, or combinations, okay? So algebraic in that sense. Not transcendental, okay? I need something which is algebraic so I can do an asymptotic series expansion. So here's my expansion in terms of a polynomial for the exponential function. I'm going to pull off this e to the 1. So this is just going to be e to the minus w eta here. And this is just all that rewritten. So now I can just multiply term by term and collect powers. So I get e to the 1 times everything. It's going to be 1. I get it. That the 1 is coming from this times that. That's the only order 1 term. The only order eta term is going to be determined by multiplying this times that. So that's where I get that order eta term. Remember, w is an order 1 variable. Okay, so in terms of things getting small, it's not. It's staying order 1. What's the next term that I can get? Well, I can get an order eta squared. That's determined by multiplying this term times 1. The next term that I can get is multiplying, well, I get sorry about that. The way I'm going to do it is I'm just going to multiply 1 times all 3 of these, and then I'm going to take this guy times all 3 of these, and this guy times all 3 of them, and then collect, okay? And then what I have left is an order eta squared term. All right, so that's cool. No problem there. I've basically kept every term. Now, what I did say, though, was when I multiply this term times that, I'm just going to collect that as an order eta squared. When I multiply this times that, that's still going to be little o of eta squared. And same with this one. When I multiply this times that term, it's still going to be little o of eta squared. So if you don't know why that's true, just remind yourself what it means from the definition. Okay, so there's that big ugly power series, or series that I had. Now I only want to keep things which are smaller than little o of epsilon. Okay, so what is going to be little o of epsilon? Anything that has epsilon in it gets collected in this guy. What does it mean to be little o of epsilon? It means if you multiply or you divide by epsilon and send epsilon to 0, that term goes to 0. Well, if I divide this term by epsilon and send epsilon to 0, do I get 0? Yes, because eta is going to 0 as epsilon goes to 0. What about this one? Yes. If I divide by epsilon and send eta to 0, sorry, if I divide by epsilon and send epsilon to 0, this term still goes to 0. What about this one? Same. Anything that has epsilon in it, it's going to do that, right? Except for the one that has epsilon by itself. Yet you need something else which is going to 0 besides epsilon. This guy is not going to be little o of epsilon, so that one stays. It's I think I said smaller than that, but you understand what I mean. Smaller than that in terms of powers of epsilon. Okay, what about this guy here? Is that little o of epsilon? Well, if I divide by epsilon, I get eta over epsilon. No, that's getting large, right? So I have to keep that term. And now I have to, so that's this guy, and this guy are below this guy. But what about this? I don't know. This could be on the cusp. So I'm going to make a decision about that. I can show in my next step, I probably should have done the inner expansion first, but I'm going to get 3 terms in the inner expansion that I have to match. So I want this guy to go away because he's not going to help me out. He's just going to be a nuisance. So what I want is, I want this term to go away. How will it go away? The only way it's going to go away is if it's an order epsilon term. Okay. So what I want is eta squared over epsilon to go to 0 as epsilon goes to 0. Because I don't want this term to be there. And you're going to see why in a moment. If this term was there, then I would be in a little bit of trouble with respect to matching. So that's the condition that I want for this guy to be an O of epsilon or higher order term. Okay, so I'm only keeping lower order stuff, and I'm collecting all higher order terms in this little O of epsilon garbage bin. So I've determined by my choosing that this guy should go to 0 when I divide by epsilon. That's this condition here, right? Because W is an order 1 term. Well, that implies that whatever is left is just these 3 terms here. So that determines the Y11 outer match. Okay, and there's no free parameters in that. So let's go to the 1-1 inner match. So here's my solution for the inner expansion up to and including the first order correction. So we're keeping the leading order and first order corrections only. That's these 2 terms. So now I have a bunch of exponentials here, but these are exponentials which are going to get small really fast. Okay? So how do I do this? This is all in terms of the z variable. I'm going to replace z with a variable that's only expressed in terms of w. Okay? So now I get a bunch of terms which look like this. Okay? Here's one which is not exponential, but all the rest basically are. Now, these terms here are going to be transcendentally small. Why? Because as epsilon goes to 0, eta over epsilon is getting large, right? As epsilon goes to 0, eta over epsilon is getting large. And this is e to the minus something large. This is getting transcendentally small, folks, right? So is this one, so is this one, and all at the same rate. So I'm going to throw in there what it means to be transcendentally large. It means it's little o of e to the r over eta to the r, because that's the prevailing term in there, for any value of r. This is going to be, as long as r is big enough, this is always going to be smaller than little o of epsilon. Okay, you might need to convince yourself that that's true, but that is true. All of these terms are going to be smaller than little o of higher order terms, okay? Smaller than little o of epsilon as epsilon goes to 0, as long as R is large enough. Doesn't matter what eta scale is. All right, so I have this beast. And notice that this beast has these unknown coefficients, or these unknown coefficients, C0, C1, C0 in them. So if I throw away all of these terms, and the only thing that survives is then going to be this C0 here, this C1 times epsilon here, and then finally C1, or C0W eta over epsilon times epsilon. That's just this term here. So those three terms are the only ones that are ever going to survive. All the rest can be collected in the garbage bin of order epsilon terms. This implies that this is the Y11 inner match function. Okay, so we have the outer match function and the inner match function, and I deliberately got rid of that fourth term by my assumption, and that fixes the size of the matching region. That fixes how big or how small eta has to be in terms of powers of epsilon. I get 3 terms here and 3 terms here, and now I can do my matching. Because this is an order 1 term, I know that C0 has to be equal to E1. That has to match that. What about this guy? This one has to match this guy, but that gives no new information. It says that C0 equals E1, but at least it's consistent. And then finally, I have to match the order epsilon term. That says that C1 has to be equal to E1 over 2. Well, that tells me what my match function has to be. In fact, it's always going to be equal to the same as what the Y11 outer match function was, because I'm matching the inner solution function to that guy. I'm choosing my free parameter so that that becomes valid. So here's my match function. So now I form a composite solution. I'm just going to take one more minute. Sorry about the time. I take my outer solution plus the inner solution up to the first order terms, and I subtract off the matching terms because I don't want to overcount. All right, so if you boil that all down, add all the terms in there, we write everything in terms of X, okay, not in terms of Z or W. We go back to X and we get this beautiful little function here. So how well does it do as an approximation of our solution? It's not hard to also get the 0-0 matching function or the 0-0 composite solution. So that one's given by this 2-term approximation here. So I'll leave those details up to you. Here's a comparison of that guy. That's the 0-0 matching function. That's the orange curve. That's the one down below. Here, the true solution is in blue. You can't see the blue because the green is basically overlapping it. The 1-1 matching function, or the 1-1 composite solution, is such a good approximation that you can't distinguish between the green and the blue. This is for epsilon equals 0.1. If I get smaller in epsilon, then the matching becomes even better. That is, the composite 1-1 solution basically overwrites the true solution to the eyeball norm. Okay, so we finished the first part. Congratulations to us. Thank you for giving me a few extra moments of your time. Are there any questions?
So the way that we match is essentially using the 3 conditions on eta and delta, like the
Delta becomes fixed once I determine the boundary layer thickness, but eta is still flexible for me. So I know.
you have like 3 conditions, like can you scroll back?
Yes. So all I need to know about eta is that it satisfies those 3 conditions. I never have to specify it exactly. Although you can do it in the usual Gauss style, right? You could say, here's what I'm choosing for my eta scale for the 1-1 match, and everything falls out beautifully, and nobody knows why you chose that value, right? You could choose it like that by removing the scaffolding and just, okay, you know the reference, right? Or you can do it this way and sort of determine the value that eta should be through this whole process. So we're going to do more complicated matching where we're going to do the 1-1 and the 2-2 match. Actually, lots of work. And we're going to see how eta changes between doing the 1-1 and the 2-2. And we already discovered this in chapter 2, but I just wanted to reinforce what's happening here in chapter 5. Okay, guys, thank you for your extra time. And again, I'll be posting homework solutions maybe late tonight, along with the good news about homework. Okay, so I'll see you guys. Have a nice day. See you on Thursday.